Next is question number 10.18. It reads, para-chlorobenzene has higher melting point than those of ortho and meta-isomers. Discuss. So here, before we jump into solving this question, we need to know the structure of para-chlorobenzene, ortho and meta-chlorobenzene. So let's draw the structure. So now I have the orthochlorobenzene. That's the structure of an orthochlorobenzene. Then we can draw the structure of a metachlorobenzene. Alright, and then a structure of parachlorobenzene. So here in this we have three different isomers at which the Cl is placed at different positions. So this is the ortho isomer, this is the meta isomer, and this is the para isomer. Now there are certain things to be looked at. One is we are going to look at symmetry of the molecule. Alright, and then we will look at steric hindrance. Alright, so here these are two factors that you will look, and you're going to determine to find out why is that parachlorobenzene have the higher melting point. So if we're talking with respect to symmetry, ortho and metachlorobenzene do not have symmetry, whereas if you take a parachlorobenzene, the molecule itself is having symmetry. And when it has symmetry, they will exactly fit into a crystal lattice and the packing will be a closed packing. Right? And because of that, when it fits right into a crystal lattice and they're symmetrical, it is very difficult to break the bonds in such a compound. Right? When we say melting point, the temperature is higher temperature is going to break the bonds. So in this case, when the molecule has symmetry and when it exactly fits into a crystal lattice, it is very difficult to break it from the crystal lattice. Therefore, you need very high energy. So that is one of the reasons why higher melting point is there for a parachlorobenzene. On the other hand, when you're looking with respect to steric hindrance. Now, each chlorine atom has three lone pairs of electrons. So I have three lone pairs here. This Cl will also have three lone pairs. So this way each Cl atom will have three lone pairs of electron or unshared pair of electron. Now when you have such a molecule with these many unpaired electrons, what will happen is there will be steric hindrance between these two. Right? And the stability of the molecule will be the least in case of ortho isomer. Meta also you will have some sort of a steric hindrance, but in that case the steric hindrance is much lesser when compared to ortho isomer. On the other hand, when you look at a para isomer, they are placed farther from each other. In that case, a para isomer is much more stable. Therefore, you have much lesser steric hindrance in case of a para isomer. Alright, so here we can say that para isomer has higher symmetry and therefore fits into the crystal lattice, therefore fits into the crystal lattice. So this is point A. In the second one, you can say they experience much lesser steric hindrance, or you can say much lesser repulsion from the unpaired electrons. So because of these two reasons, parachlorobenzene will have a high melting point, and because the melting point is high, the solubility is going to be low. Alright, so this is how you come to a conclusion whether you want to decide whether one isomer is having a higher melting point than the other. Alright.